came from Arnie, who I there. So Arnie gets, what prize should we give Arnie?
Oh,
You wanna pick one?
yeah, sure. Like, what's that? I
Those are
don't know.
socks.
Okay.
Looks always good.
They say,
Thank you.
do you wanna read what they say?
They make up everything.
Atoms make up everything.
Oh, there we go.
Okay, so.
Including those socks.
Can quantum computing be a competition for classical computing?
Yeah, thank you, Arne, for the question. Like, can quantum computing be a competition for classical computing?
Yes, is quantum computing competitive to classical computing?
Yeah. And
Which opens up a whole can of worms, so go ahead, you just grab that small question.
it's a tough question, and I would say like the answer is a mix of a yes and no. and I'll really answer that question. I'll start with the no. Like if you look at quantum computer today, like you'll always have like racks of control electronics, like classical compute, sitting next to the quantum processor. So like you need classical compute to control the quantum processor. You need the like classical compute to correct for errors, and also maybe a second reason why it cannot like replace like quantum is not going to be a competition like in the short term is that quantum computers are highly specialized tools, and you can think of them as like, and the analogy comes from like a panel on which my co-founder of Alexander was last week. Like you can think of quantum computers as like a lightsaber, and if you take that to cut like butter, it's not going to like be efficient. Like just going to like all the butter is going to melt. So you need like just a normal knife, and so quantum is going to be specialized, and I believe Joshua is going to talk more about that later. But you'll solve very hard and intractable problems, but you're not going to like do work on spreadsheets on a quantum computer. So that's the second reason. That said, if you think of competition like at the investment level, I know like there might be some investors in this room. Like investments, like capital, they go where the new capability is, and quantum computers, they are going to like add a lot of value on top of things that might be commoditized. I mean, like CPUs, GPUs will need them, and but they are still very innovative. But quantum computers are going to bring that like additional innovation, and capital is going to flow into quantum for that specific reason. There are like other geopolitical reasons why people invest in quantum. Like you can run Shor's algorithm, or governments want to like break like crypto systems of some like potential adversaries. But like the fundamental reason driving the economics here is that quantum can like solve problems that cannot be solved otherwise. And also potentially in the future, when quantum is going to develop, it's going to be like economically more relevant. Like you get an economic advantage, and also it could be energy efficient. So these are like different reasons. So I would say like in short term, it's definitely not going to replace classical computers, but it can compete at the investment level. And in the future, it's like early to say yes or no, but it's going to be a serial part of the compute mix. Like it's going to be part of the compute mix of like all the businesses. That's for the answer.
No, that's, anybody have any questions? Because we have a part 2 to that, which I think Joshua's going to answer. Which domains are ideal to apply quantum computing to address today's challenges? So that kind of, you just queued up that question. Is Brandon Hunter-Lee in the room? No? Okay, no prize for him.
Can I say a few words on his first
Sure,
question?
yeah.
So I interpreted this question slightly differently, and thus I fear I interpreted it wrongly. But we'll go with what I was thinking of. So as is probably familiar to hopefully lots of people, especially those in the quantum space, do we have a lot of people like in quantum computing proper here? Raising hands. Okay, so majority not. Okay, cool. So whenever we talk, so Victor's absolutely right in terms of like developing an ecosystem with all of these different facets, right? Where you're never going to have your phone in your car run a quantum computer. You don't want that, right? But again, as standard in the industry, we're always looking for those applications where quantum computers demonstrate a proper advantage, and what we're explicitly comparing to is a classical benchmark, a classical method at the cutting edge, right? And so that is, the famous random circuit sampling experiments, tensor network simulations, and what have you in lots of different contexts. So my answer shortly would be yes, because that's the sort of the premise by which we define quantum advantage, sort of the boundaries of them between where a quantum computer is useful and where a classical computer is useful. I like to think of it with ever greater levels of precision, like an axe, then a knife, scalpel, then a laser. We're sort of drawing this boundary, which begs the question of like, well, what does it mean for a classical algorithm to compete with a quantum algorithm? How do we actually define what advantage looks like in between those two things? And my general take on from my understanding of the literature and such is there's sort of 4 dimensions by which we can categorize advantage, and one is the sort of a comparative performance statement, right? This is where the scaling arguments come, right? The speed ups and all of that language lives. And there's typically a triple between like some space-time resource that you're comparing, time or qubits or what have you, and then the classical benchmark, and then the scaling law that relates from that. Within that, there's a sort of ongoing battle that of, well, you're always, it's a little heuristic, you're always comparing to the best classical methods, and well, we come up with new ones all the while. For those of you familiar with the Fumoko experiment, famously, we have classical simulations of that have trumped, the advantage claim of the past 5 years. But within that, if you would like to make some type of comparative claim to all possible classical algorithms, in my mind, that's where like complexity arguments exist. So for those of you familiar with BQP or QMA complete, that kind of language to me lives in that space. Pair that with second axis, which is accuracy, and so it's all of those things, but for a particular accuracy of the observable that you're interested in. And those sort of two things work together. And then third, slightly more niche would be like sample query models. So like understanding that a fair fight between a classical and quantum computer, you need your classical machine to sample in the same way that a quantum computer does, and that often closes the gap. A little technical, so we may not go into that now. But and then the third is, can you actually verify the answer that a quantum computer gives you? If you can verify it, that's a stronger advantage claim than an advantage claim that you can't ultimately verify. There's a lot of nuances there. So that's sort of my follow-on to that.
Is there, we talk a lot about drug discovery and development and stuff like that. We talk about the intractable problems like neuro dementia and stuff like that. I think we're going to get into crypto in a few minutes, so we won't talk too much about that. Is there any other kind of, we can't do this now, but we hope to do this with quantum that can be broadly, talked about?
Yeah, and
We'll do that later? Or?
No, I'll do that right now, and I'll fold into, because there was a second question that you asked me. So in terms of like the most viable applications that we see on the horizon that have the strongest advantage claims is in cryptography and quantum simulation. And in terms of those intractable problems that Shane, you mentioned there, I'll speak on quantum simulation because that's what I'm most familiar with. We two general buckets of like solid state physics, condensed matter, and quantum chemistry, molecular simulations. And broadly speaking, it's choosing systems with sufficiently high entanglement, right? For solid state systems, it's are you near a phase transition? You have a frustrated or disordered system, something like that. Molecular systems are really interesting. I'm not an expert in this, but it's the emphasis there seems to be on like really precise numerical predictions, like this is 3% better versus 1% better, and that seems to come down to like more dynamical questions. So those are like particularly intractable. One final tagline will be like the paradigm historically has been like ground state, but now we're shifting to more of a dynamics of quantum systems and excited state dynamics and things like that, as opposed to just ground state stuff, because tensor networks rock with that.
Well, go ahead, yeah, and then we'll go on to the next question.
Because of that, like we published a report on what's quantum computing going to bring for high performance computing in general, and we were listing the different most promising applications. And if you you want like an order of magnitude of like the impact on the most promising applications, we looked at different data points from the national labs here in the US. So you get like Los Alamos or Lawrence Berkeley, or like systems that are hosted at Oak Ridge. And these systems, they run like scientific computing all the time. And like if you take the applications that can be accelerated by quantum computing, you find out that it represents up to like half of this compute time, maybe more, because you get more people like finding applications in the future. But it means like really like you can accelerate with quantum computing or enable. Like there's a debate on the term, can you accelerate? But like you're going to enable computations that cannot be solved otherwise. Like for applications that are of interest to like more than 50% of what the Department of Energy or the high performance computing community is interested in. So it's a huge impact.
Okay, one tagline on that is the developing applications for quantum computing is an open field of research. I think that the general trend within, this was a discussion at Google's Quantum Summer Symposium a few weeks ago, is that we're at somewhat of an inflection point where, like, if you handed us a fully fault-tolerant machine right now in this moment, we actually wouldn't know what to do with it, beyond a few cherry-picked examples, right?
Yeah.
So,
When you're done,
Victor, Joshua, great. This is amazing. But back to the question about quantum computers versus classical computers. Joshua, you mentioned random circuit sampling, and I know that recently Quantinuum and I think it was J.P. Morgan, they did an experiment where they certified randomness. They created random and unpredictable data from a quantum computer, and they tested it utilizing a supercomputer, and it was verifiable. This is something that a classical computer cannot do. So quantum computers today can still do things that classical computers can't do. And with that, there are applications, right? Randomness is a part of our everyday lives, right? All of our cell phones, our Apple Watches, our computers. So do you see randomness being a major aspect of quantum in the future? A major application of quantum in the future?
it's a good question. Victor, you want to kick us off there?
Yeah, it depends on it depends on costs. Like certifying, like generating random numbers with a quantum computer is like very costly today because quantum computers are very costly. So like if you want to like use quantum computers for that, like maybe there is like of course like there is an application there, but like I'm not an expert in this specific application field. But so far what I understand is that people have been using this application as a way to demonstrate that quantum can beat classical compute, and we need that. And also like demonstrating that it works. But yeah, I think in the end it's all about like what's the economic trade-off.
Yeah, and to add to that, so like the terminology I'd like to use is, so those RCS experiments are super critical for demonstrating like scientific advantage, right, versus commercial advantage. And we're sort of right on the cusp between those two things. So scientific advantage is like, just showing that there is a context in which quantum computing beats classical computing. And you're exactly right, this absolutely happens, right? And to go one step further, Google had, we had this, the Autalk paper, the very famous Autalk paper from last year, then applied to NMR contexts, right? So there is absolutely a pressure to try to find things now, but and this gets to the whole conversation around the NISQ era, right? It'd be cool to demonstrate those things now, but NISQ is definitely just a temporary waypoint, and you can kind of see that as signal, especially like in job postings, like more than half of them are for error correction because the industry is just doubling down on fault tolerance because that's where most of the interesting things lie. But going back to your question about randomness, I know there are some, I don't know them off the top of my head, but I know peripherally there's some niche applications of random circuits specifically. I'm not too familiar with them, but my understanding is that's not the flagship application for quantum computers. It's typically within the realm of either quantum simulation or cryptography. RCS was always sort of a somewhat artificially constructed benchmark just to demonstrate that it can happen.
Isn't randomness a core aspect of cryptography?
Oh, sure. I mean, there's definitely but I don't think RCS experiments, as far as I understand them, are directly addressing the randomness in those applications. Is my
I've got
understanding.
a reference for you, like, can share that later.
There we go.
On randomness.
Yeah, I mean, because we're gonna talk about security in just a few minutes, and you wanna give them some stickers there?
Yeah, sure.
All
Yeah,
right.
like-
Yeah.
Physics stickers, everybody needs physics stickers, yeah, good question, good question. So building on that, idea of science, you know, applications, so the next question that we have from Myron, who I think is in the, yeah, there you, okay.
Ask the question.
Yeah, you did. You actually asked a two-part question. You said, when will quantum cross over from curiosity to commercial application? So we kind of just talked about that. You could add to that. But now we're going to get into the really interesting thing that everybody wants to know: is my computer going to get hacked? And the cryptography applications, because there's a lot of fear around around that. So why don't we move into that, and what should we give?
No, there is.
Can we give out the, oh, yeah, this is a cool
Do you
thing.
have, has everybody seen this? Are the, this is by, Yuval, who's over at Quora, and, they are little, what do you call them, cartoon, descriptions of quantum concepts, and they're really well done. You'll see them online, they get posted every so often. They just came out with 2 books, which you can get on Amazon, and I think it's fantastic for those of us who are like, wow, this stuff is like, he does it, he breaks it down in a really nice way, and so highly recommend. It's called Quantum Bits, if you want to pick it up. And Mary, you get a copy today, you can bring home and read.
You should call it Quantum Dilbert.
Yeah, exactly, yeah. All right, go ahead, you, from commercial into, cryptography.
I'll start and I'll kick you off the cryptography stuff. Yeah, so like in terms of general timeframes, which is always the hot topic of conversation, just judging by like general roadmaps, some more aggressive than others, but we're like looking at a 5 to 10 year timeline. 5 years, you know, plus being the arrival of fault tolerant machines. One thing that's particularly exciting with Google is they are incorporating neutral atoms into their superconducting everything, and that's ultimately going to fit into this, which is beyond me in terms of the hardware, this modular, scalable structure. So they were able to demonstrate error correction recently, so that's one, and then the next step is scalability. And then commercial, like truly commercial applications, you know, let's go 5, you know, another 5, so 10 on that. And really what this is in my mind is that there's like 2 phases to this, is, and I'm capturing both cryptography and simulation among others, is we have these pilot testing spaces that is just true experimentation in science and investment, and then plugging it into existing workflows. So it's like 10 years we can see like really incorporating into like upending industry workflows by my estimation. But one thing I wanted to plug is Victor's Quantum Times recently did an excellent article on the timeline of cryptography specifically, which also has a similar 2035. So if you wanted to speak on those 3 stages in your article, they were very educational to me. So
Yeah, so Quantum Times is like a media I recently launched with like a friend who's working for Quantum Nation. It's the like largest investment fund for quantum technologies at the VC stage. And like we published an article like raising the question like, what are the different scenarios in 2035 with like, do we have a quantum computer or not? And is post-quantum cryptography migration like delayed or not? Like, is it there? Like, is it completed or not? And like, you get like 4 different scenarios. Like only like selected 3. So first one is you don't have a fault-tolerant quantum computer, and PQC migration is like anyway, like you don't care because you don't have fault-tolerant quantum computer. But even in that scenario, there is a risk in the fact that the migration to post-quantum cryptography, if not well realized, is going to bring new threats because you still have classical computers that can break like encryption. So, and also, like, you know, you got like the Claude Mythos like AI tool that was very efficient at finding like loopholes in crypto systems, and like this migration if not handled by experts, they are going to like bring regressions. And so there was that paper from Google that came out like a month ago. It was very, very interesting. Like, okay, like even like the migration itself can be a problem. Like even if we are not even talking about quantum computers, but right now you need to migrate because like the threat is real. But like if you migrate, like should be wisely done. And second scenario is you get a quantum computer that's not powerful enough to break cryptography, and no, sorry, you get a quantum computer that's powerful enough, but migration is completed, and in that case scenario, like same, you still have these like risks in the migration, but also you're exposed to harvest now, decrypt later threats. So like all the data you got today, if not migrated today, it's going to be exposed in 5 to 10 years. And last scenario is you get a quantum computer that's cryptography relevant, and migration is late. And in that scenario, like it's kind of like chaos. So I encourage you to read the article, and we also published a fictional intelligence piece just last week on the second scenario. Yes, second scenario. So it's a project I do. It's my night job, I would say, and it's really fun.
And
So-
the way to get to that is you have a website, which is quantum-times.com.
Yes.
But I like to see it on LinkedIn. So
Yeah.
if you're connected to you'll automatically see those posts as well. So there's a little.
I just want to add a couple taglines to that real quick. So the one important thing about this elliptic curve cryptography paper from Google that Victor just alluded to, that's super important is, so they were developing these different algorithms for PQC. They have this whole excerpt at the bottom about, this sort of tension between, well, if we release the details of this, right, it'll reveal vulnerabilities that people can then exploit. And so the revelation for me that I have yet to look into, I encourage you all to look into it along with me, is the use of zero knowledge proofs, which is a field I'm not familiar with, but they, at QSS recently, they were discussing the use of zero knowledge proofs as a way to reveal, partially, somewhat, the methods that they're using for PQC without exploring vulnerabilities. So, and this to me sits into the underbelly. This is a phrase you coined from the article. Like, it's not in the Q day; it's in the Q transition, right? Q day being the day when everything is unlocked and then we all lose our money, right? But but it's in the Q transition where we are converting over the systems over the next 10 years, which I believe the government has already started doing. Is that correct? Yeah, with the new NIST protocols. But yeah, anyway, Shay, please continue.
I think that answered the question, but we're going to give, if he's here, we're giving the credit. How will the security world shift with quantum? I think we just answered that. Daniel, are you here from Northeastern? Daniel Su? No? Yes? Oh, okay. We're going to give you, yay.
I also saw.
You would learning all fun. There you go. Okay. Go ahead. Were you going to say something, Josh?
No, they just they had a
Oh,
here.
go ahead. Question, go ahead.
Could you comment on the timeline and the use of quantum communications with quantum process?
Oh, right. So I just feel I know the least about, so forgive me, Victor. Thank you.
Yeah, thank you. Hard question. I would love to give you a more educated answer. So, we can connect and do like a few research now, give you an answer, because I don't want to say crazy stuff. It's not my field of expertise. What I can tell you is, China is making good progress on quantum communication, and we might need quantum communication, to be safe in a world where you have quantum computers, just that the infrastructure to develop a network of like a quantum internet, it's like a quantum internet, if you using quantum communication, like hardware, that could be very expensive. And the last point is what we would see from the quantum communication field as an interesting application in the very near term is interconnecting different quantum computers to increase the power of the quantum computation. So it would use like similar technologies to exchange quantum information between distant quantum computers. That's what Cisco Cisco is working on, IBM has been partnering with them, Argo National Lab as a program on that. So like you've got like different aspects of quantum communication, but happy to get back to you with like more insights.
And one other tagline would be like the quantum communication could be used as a bulwark against the threats in the traditional cryptography space. So there's some, using some algorithms within that field could provide more security in the more traditional context.
And you had a follow-on question or a comment to make?
Quick question. So
Okay.
when you talk about like threats in the quantum space, what do you guys see as like the agents who would actually be doing that? Because obviously quantum has like very high startup costs, and mainly the big tech companies and governments who are developing the technology. So is there a risk that if quantum becomes more successful, that smaller agents will be able to have that type of infrastructure, or is it mainly from large corporations and governments?
I would think like all democratization of technology, we see this in the biology space as well. Like definitely, as the technology gets better and better, it becomes more accessible to more people. So it definitely depends on how the hardware scales. They're definitely still pretty darn expensive, right, to operate. So I think my guess was within the next 10 years, it's mostly within the big players of the world that have access to the technology. But certainly in principle, your intuition, I think, is correct.
The fictional intelligence piece I was mentioning on the scenario where we have quantum computers, but migration is successful, is that like quantum computers could like remain behind locked doors, and like people want to get access to like democratize access, because it's likely like governments are going to be the first adopters, even if you've got like big corporations. Like we have a partnership with General Electric and big corporations in Europe as well, and they are interested in having access, but like in the end, governments might also be interested in acquiring these machines, and you've got like more and more export control. So like this is a fictional scenario where like quantum computers remain behind locked doors by 2035. So, but like still fictional.
These questions are great because they lead right into the next question. And this is something we think about with AI a lot, and we're going to talk about quantum and AI in a moment, but how do we solve the issue, it was mentioned a little bit ago, of energy consumption and supply of these computers. Catherine was just saying that when Atlantic Quantum was here, they were using like all of the energy that they had, right? What did she say? She said it was like at least 20% of the building's energy at any given time. Campbell Square's not really known to have a great grid. Like, can you talk a little bit about the impact of that, in light of what's going on with AI as well? I'm going to give out some stickers.
Yeah. So just quantum computers, indeed they consume energy, and but you've got like a broad like a range of energy estimates depending on the hardware that you're using to perform your quantum computation. So it could range from 100 megawatts for performing like a useful system to a few hundred of kilowatts. So depending on like the hardware that you want to use, the energy cost is not going to be the same. So you could get like an energy advantage for like the quantum computers that are useful and that are also like energy efficient, but like for the biggest like quantum computers that are very energy greedy, you wouldn't get like an energy advantage, but you could still get maybe an economic advantage. It all depends on the cost of energy, because the rule of thumb is like a megawatt of energy in the supercomputing business. It's like a million, like maybe more, like between $1 million and $2 million US dollars. So like if you just like think of a quantum computer consuming like tens of megawatts, like the scale of like the biggest supercomputers out there, like then it's like going to add a significant like line to the total cost of ownership of these systems. So like you need to think about that, and there are different initiatives. I want to mention the Quantum Energy Initiative that was co-founded by researchers, but also like companies, and it's doing a great job at like integrating the cost of energy inside the design of quantum computing. And I'll stop there.
Yeah, I'll just add a few notes to that. So I think another high-level thing for, again, those not within the quantum spaces is the energy consumption is highly hardware modality dependent. So we have all these different companies that do superconducting, neutral atom, trapped ion, and the energetics are highly variable across that space. So I think the one quick easy answer is that it's not so much the qubits themselves, it's everything supporting the qubits, right? So the superconducting space, it's the dilution fridges, right? Getting to our millikelvin scale. And then for trapped ions and neutral atoms, it's the lasers and things like that, and the vacuums that are involved there. In anticipation of this question, I Googled it. And there was a very recent paper that was attempting to do energy estimates on this. And you know what I'm talking about, Arne?
Yeah, I wasn't convinced by that.
Wasn't convinced? Yeah.
No.
Yeah. What were your thoughts on this?
I haven't read in detail, but my takeaway was that they're using current energy consumption and just extrapolate it in the future without looking into the scaling, the laws of scaling too deeply.
Yes. Okay. Fair enough.
Can I add another question inside that? It's just the total environmental impact seems not to be quantified within that, all the other resources that go into the energy consumption.
Right. Yeah. Absolutely. It's the important thing within.
Just like water, for example, like.
Right, exactly. And that was where I was ultimately building to, is that you have to have an end-to-end resource estimation not only with algorithmically speaking, but also within the idea of energy consumption. And that has to be application specific. And this ultimately gets to the idea of commercialization ultimately, which is what we all care about at the end of the day. Well, the first and foremost is not so much does it have an advantage, but does it solve my problem better than a classical computer could, right? And embedded in that question first is all of the algorithmic and scientific questions that we want to answer, but then it's well, from a business perspective, is it going to cost me more money? Even if it gets me a better answer, it could still cost us more money, right? And so there's a specificity that's required there that I think is a lot more work needs to be done in this, so I charge you all to go do that homework exercise left for the audience. But it's more complicated than just how much is coming out of the outlet right here.
Yeah, and one thing that quantum hardware companies should be doing is estimating what's going to be the energy cost of their own quantum computers that they are building. And that's something we've done at Alice and Bob, and we estimated that a machine with 100 of very, very good qubits, it would be 160 kilowatts. So with that kind of machine, you can start tackling problems that are out of the scope of the biggest supercomputers, so consuming several megawatts. So in the end, you get an energy advantage. You also get an interesting application that you couldn't do otherwise. But some other quantum vendors have been doing that work, and it was trying to understand okay, what are the variations here, and how's the scaling as well, because the scaling matters a lot.
Are you saying that you're using quantum computers to work on quantum computer problems? And if so, what problem would you select to put your quantum computer on?
Oh, so that would be for applications in solving condensed matter physics problems with that size of quantum computer I was referring to, between 100 and 200 very, very good qubits. But Joshua, I don't know if you want to talk more about that.
Yeah, I mean, with regard to, if I understood your question, we're talking about applying quantum computers to just quantum physics problems in general, the simulation question.
Yes.
Ultimately, I think what's really important, I have two thoughts on that. One is in terms of finding, again, an advantage claim within there, you have to make sure, so I alluded to earlier about having a sufficiently highly entangled state. Well, there's lots of states within, highly entangled physics states within condensed matter that actually undergo thermalization, so that most of the observables that you care about within that actually settle on these fairly predictable values that a classical computer could output, right? And so the analogy is a little bit like temperature in, it's coming from in a normal, this room. The gas in this room is, some super, if you were to, simulate it, it's some, random process of collision of molecules, right? But, well, if I'm trying to just predict the temperature, I just need a thermometer. I don't need to simulate the entire bit of the room. So it's a little bit like that happening, but for condensed matter systems. The second thing, with regard to like scaling that you were alluding to, Victor, is to me, I think scaling arguments, even though that's the standard playbook of determining where to apply things, I think scaling arguments are less important in that context because ultimately molecular condensed matter systems, they have finite correlation lengths in the interactions that obey this, that the system undergoes. Like, there's just a limit to how far in the system those interactions are happening. So it's less about like what's happening in the limit of infinite qubits and more like in a particular case at a particular qubit count, because the correlation lengths are finite, what's happening, you know, between a classical and a quantum computer. A little bit of stray away asking, but hopefully that addressed.
I've got some serious, we have 2 more questions, but I'm gonna pause for a moment because we have about 10 minutes left. And I know that we have a diversity of backgrounds and interests here. And I wanna just open it up to the audience. Does anybody have any questions? They can be generalist questions, they can be more technical questions. We can play Stump the Speakers, but also, you know, quantum can be daunting. Okay, Vineet.
So if you had to dig into your savings and invest, let's say 50% of your savings into a quantum computing startup, what would that look like?
Are you writing checks?
My company,
That's an awesome
I'm investing my like most of my time for that company, so that's I'm working for a company.
But one should diversify. You shouldn't put all your labor and your capital into the same company.
I think like if you look at an interesting approach is what NVIDIA is doing. So NVIDIA, they understand like, okay, it's early to say who's going to be the winner because there might be like different winners at different stages, and also in terms of maturity. And all like quantum hardware is not like on the same like level when it comes to maturity. And some modalities can like be like apparently lagging behind today, but they can catch up very quickly because the scaling is looking very good. And so NVIDIA, they've been investing in different companies, like different modalities, PsiQuantum, Quantinuum, Qujera, and Alessandro. So they are like, I think it's an interesting strategy. I would still go for Alessandro because that's where I'm spending most of my time, and that's also the company like where I know the roadmap and the what's been done in the lab, and you know, like everything is not like fully transparent. So like from an external point of view, sometimes it's hard to see what's happening in the labs of the different quantum startups. But yeah, I think like IC Direct, they are doing an amazing job as well in the audience, and so it's also a good quantum company. Can watch out what they are doing.
Alison Labs is a French company. Do you have a U.S. subsidiary for those that might want to invest in the U.S.?
Actually,
could that happen?
Yeah, that could happen. And we actually got like funding from NVIDIA via NVentures, just that was announced last week. So
Yeah.
I guess that's.
And we want to build your presence here in Massachusetts too. So.
Yeah, in Massachusetts, like in all the states, and had very interesting conversations with like all the U.S. like partners.
But you like Massachusetts the best.
I love Massachusetts.
Just want to put that out there.
I love
Guys,
Cambridge.
we gotta keep companies like Alison growing here in Massachusetts and other states as well. Question in the back.
So what do you think about the impact of the public markets on this sector? You know, we've seen SPACs and we've seen a lot of retail demand, perhaps sometimes a little bit ahead of where the technology is. I imagine there's good and bad. I mean, they can also buy the startups, but we're like particularly focused on the startup and the VC angle. Is it helpful or is it kind of hurtful?
Can you just specify a little bit more of what you mean by this?
Yeah, like just having a wave of SPACs and then having like very heavy retail demand that can push volatility on some of these names, like IonQ and that competitor set. Do you guys view it from the startup side, from the side of the VC backers? Is that helpful for the space or does it cause issues?
Is that a hype question in some ways?
In some ways.
Yeah.
And just for somebody else in the argument, certainly not me, what's a SPAC?
Special purpose acquisition company is kind of a quirky public market thing where you take the vehicle public and then you have a deadline to go acquire a company to fill it with, or sometimes you could put multiple names into the SPAC entity. They've got a bad reputation because a lot of them have traded pretty horribly and caused a lot of retail investors to lose money.
The question, it really is a question, kind of, I wanna say SPACs being, SPACs come and go and popular and stuff like that. And I kind of, if I was to pare back the question, tell me if I'm getting this wrong, is you're seeing these crazy valuations now, right? You're starting to see, and are they, as two folks that are deep in the industry, are you like, well, woohoo, this does good things for the companies that I'm involved in, or are you like, yeah, the potential is there. It's like the potential is so strong that these are still, there's a lot of opportunity out there, there's a lot of potential. And then creative vehicles like SPACs, we can debate about how creative they are, but are becoming popular to take advantage of that perception. And some of that falls, we didn't get to that question today, with what AI is doing right now, the valuations of AI, and is quantum the next big thing. And I don't think one necessarily is the other way to get to that question.
Yeah, so
it's more of like hype versus reality.
Yeah, so I'll give my best stat here. So basically, I think the historically speaking, right, this is what I believe is called a strategic investment, right, where it's like you're not looking for returns to come within the next 5 years. It's greater than that, right? So I think there's from an investment standpoint, there's what I would call like smart money, like just recognizing that the return on investment is not something that's coming immediately. So I think in the spirit of like hype and being really sober-minded with respect to the markets, starting there is like a super important thing to like always touch grass. And then I would say like the startup space is very tricky because it's an experiment within an experiment. Again, going back, so a startup is inherently an experiment, and then I alluded to earlier how a quantum computing workflow fits into an existing industrial workflow, right? That it's like ideally what we would like is to have sufficient proof of concept on the hardware side. So again, 5 years, right? Plus or minus. That we have enough confidence in the hardware that then people can start to play in the startup space of like, oh, let me do a startup that actually incorporates a quantum workflow and then see how that goes, right? But to do that right now, at least by my estimation, would be premature. And again, that's specifically for trying to incorporate it into an industrial workflow. Now, to go on the other side of this, at XPRIZE, what we're pushing for in this last phase of the competition, but the second phase is about applications specifically, is we want to see how far they can get to integrating into an existing workflow. It's a super hard thing to do. We don't expect them to get to the end zone, but like the FOMOCO simulation, right? The rights for nitrogen catalysts, right? And so it's like, well, how, like, plug that into an actual pipeline? What's the effect on the process, right? So I would think sober minds are thinking about this in 5 years, not right now, with respect to full workflows. If you're just talking about algorithm startups, Europe is booming with that respect, which is awesome. I think I saw an estimate of like 10 billion or something like that. So yeah, but the work in Europe is extremely well. Look at Phasecraft, they're in algorithmic, they're doing exceptional work.
All right, we got one last question from the audience, one last prize. One of you can explain. There's a cat in there. Is it dead or alive? So while you explain that, we're going to take a question from the audience. One really good question to wrap things up today. Anybody? Somebody's going to. Okay. You got it.
So you talked a little bit about the applications of quantum to like industrial settings. Have you seen any development or investment in like developing scheduling algorithms or like multi-constraint objectives, job scheduling, things like that?
Is that, you mean broadly within like optimization?
Yeah.
Yeah. So
like specifically with a lot of the scheduling algorithms that take a long time to solve and can't be applied within a realistic timeline.
So I'm not aware of like any, Victor, I would want your take on this. I'm not aware of any like particular implementations that are happening right now, but I will say our competitors in the competition do have some very promising algorithms for optimization in particular. So again, going outside the context of cryptography and quantum simulation, just general partial differential equations and just linear system solvers which is in the spirit of, I think, what you're talking about. We are seeing definitely a lot of work happening in that space. It's just, again, it's coming into a workflow.
Okay, before I hand this over, can one of you want to explain to why I was talking about a dead or alive cat?
Yeah,
Do
so
you
it's,
think
it's in the interest of the cat, I'm not gonna open the box because I want to give it a chance of being alive. So basically, it's the thought experiment of, put forward by Schrodinger's cat, of, it's in a superposition, which, as best as we can understand, it's kind of existing in two ways at the same time, right? It's like the light switch is either on or off, and it's not in the middle between those two things. No, it's somehow both on and off at the same time. And if you think you can wrap your head around it, think again, because no one can, right? Myself included. So it's sort of an analogization.
All right, I'm gonna do that. I'm gonna hand this over to you. Thank you, everybody, for being here. This was great. I hope you learned a little bit. I hope you learned a lot. You are all part of our quantum community now, and I'm so thrilled to have you there. Feel free to field questions. We'll send a follow-up email so you can get in touch with these guys via LinkedIn. Put October 28th on your calendar. We are going to be looking for interesting research to present there. So if you know somebody who's doing something interesting, you're like, they really should get in front of a group of investors and others, please do that. And feel free to get in touch with me as well if you have other ideas as to how we can support and build our community in this wonderful quantum world that we're creating. Thank you very much for being here, and thank you.